Good afternoon. Right. We are looking at Lagrange equation, and I start considering it again today and then applying it to a couple of situations. Okay. So Lagrange equation and its applications. The Lagrange equation for conservative forces and velocity independent potential, which is given as velocity independent potential, which means that the potential function is independent of the velocities. Velocity independent potential. And the Lagrange equation is given as the time derivative of the partial derivative of the Lagrangian with respect to kth generalized coordinate, which is qk prime, the dot, time derivative of that. Okay, it is equal to partial L over partial qk, where qk is the kth generalized coordinate. Okay, so what happens is that this equation, when there are non-conservative forces that are present, this equation it takes a slightly different form. So I'm just going to write down that without going into detail of deriving it, and then start looking at how it is applied. So Lagrange equation when non-conservative forces are present, and this is written as d over dt of, again, the partial derivative of the Lagrangian with respect to the time derivative of the kth generalized coordinate, which is qk dot, is minus L over qk. So you have brought this right hand side to the left with a change of sign, and then equate it to qk prime. What is qk prime? Is the non-conservative, for instance, the frictional forces. I am not going to in detail into that. This is just a mention, non-conservative, for instance, the frictional forces. QK. Okay. Okay, now I'm going to look at what we started to look at in the last lecture, but we didn't finish that, and this was the single particle in a central field. and apply Lagrange equation to that. So single particle in a central field. Okay, so this is some situation which we have considered with reference to the Kepler's planet laws of the planetary motion. So the situation is this one, that the particle moves in a plane under a central force. The particle moves in a plane under a central force, and you know that the central force is a conservative force. So central so the so as we consider this situation, that for instance this is our particle here. Okay, and this is the r distance of the particle from the origin, and this is theta. The radial vector, it makes the angle of theta with the, you can say, the axis, which can be taken as the x-axis. Okay, now for such situation, what you do is that you choose the polar coordinates. Choose the polar coordinates as your generalized coordinates, the first thing to do. Choose the Okay, choose the polar coordinates as the generalized coordinate, which mean that the select q1 to be r and q2 to be theta. So it means that the polar coordinates are the generalized coordinates in this situation. Right, so if here we are having r to be the radial vector of this particle here, then we can write down the x as r cosine theta, y as r sine theta, and if you want to obtain the time derivatives, x dot is given by r minus sine theta, which, so I am differentiating x. Okay, so I'm keeping r, differentiating cosine, and then I need to multiply it with theta dot. This is the time derivative of x. Okay, then I can differentiate the r, which is r dot, and keep the cosine theta, right? And then similarly, so this is the time derivative, and this is the time derivative of y. Similarly can be obtained by keeping r, differentiating sine theta, which is cosine theta, and then differentiating theta with respect to time, theta dot, plus if you now do the differentiate r with respect to time, r dot, and then keep sine of theta. So you can find x dot and y dot. Okay, and now the kinetic energy of the particle is given by half mv square. So let me consider that the T is the kinetic energy. As you know, it is half mv square, and half mv square can be written as half m v square is x dot square plus y dot square, which is the kinetic energy, as you know, right? And now it is can be rewritten as half m, just simply substitute x dot and y dot. Okay, so from these right hand side, so what we have obtained here, Okay, so you just substitute them here. It will become, if I can put the brackets, so it become minus r theta dot sine of theta plus r dot cosine of theta square plus r theta dot cosine of theta plus r dot sine of theta square. So this is what I have used in here. Okay, now if I expand these squares, what I get? So if I expand this in order to obtain the expression for the kinetic energy, I get half m. So expanding the square term will give you r square theta dot square sine square of theta plus r square cosine square of theta minus 2 r dot theta dot sine theta cosine of theta. Okay, so this is the expansion of this, and now you consider this expansion. It gives you r square theta dot square. Okay, so just make it more clear that this is theta dot square, right? And then it is the cosine square of theta plus r dot square sine square of theta plus 2 r dot r time r dot theta dot sine theta cosine theta, bracket close. Now you can see that you can cancel this whole term with this whole term, okay, when you are adding up together, and you are left with, so you are left with 1/2 m, and it becomes r square theta dot square if you take out this as a common factor, okay, from these terms which are just above. So inside the bracket becomes sine square theta plus cosine square theta. Yeah, and then there are later two terms above and below, and it can be written as r dot square sine square theta plus cosine square theta. Okay, so it becomes half m r square theta dot square plus r dot square. Also, we know that the potential energy is a function of the r only, radial distance. Okay, so it is the potential energy is a function of r only. And now if you look at the Lagrangian as we define, it was t minus v. Okay, so it will be t is half m r square theta dot square plus r dot square. Okay, this is from here, from just above. Okay, from here, and then there is a minus, then vr. So this is the Lagrangian of the particle moving under the central force. Okay, now consider the Lagrange equation now. Okay, consider the if you consider the Lagrange equation, what it tells you, d over dt of partial L over partial Q k dot minus partial L over partial Qk is equal to 0. And also, uh, the generalized coordinate are q1 is equal to r and q2 is equal to theta. So in that case, okay, we find with reference to the Lagrange equation, what we find now is because your generalized coordinates q1 and q2 are r theta, and here we have partial L over partial q uh, dot and also partial q. So what you need to find is partial L over partial r dot, because this is one, r is a generalized coordinate, the first one. So what you find from this, so it is from just the equation above, which is given by 1/2 m. So you are differentiating this part with respect to r dot, partially differentiating this part. Okay, so if you differentiate this part with respect to r dot, what you get is partial over partial r dot of r square theta dot square plus r dot square. Okay, and minus partial VR over partial R dot. And of course, this is going to be 0. Okay, so you're left with 1/2 m, and when you differentiate this, this becomes 2R dot. So it becomes mR dot. I call this 1. And likewise, if I now find out, likewise, if I find out partial and partial over partial theta dot, because this is involved here. Okay, because you know that the theta dot is also, okay, theta is a generalized coordinate, and you are differentiating, partially differentiating L with respect to the time derivative of the generalized coordinate, which is theta in our case. Okay, so it becomes 1 over 2 m partial over partial theta, and we have got L, which is here, so this part. So it becomes r square theta dot square plus r dot square minus VR over partial theta dot. Of course, this is 0, and you are left with 1/2 m. So if you differentiate with respect to theta dot, this then reduces to r2 theta dot, and which becomes mr square theta dot. And also in this we need the derivatives of the Lagrangian with respect to the two generalized coordinates, which are q1 and q2. Remember that k is varying from 1 and 2. So just I put this in that a remark that k is 1 and 2. Okay, so corresponding to that, you have got these generalized coordinates. Okay, so here we have got partial, sorry, this is L here, and now we similarly find out partial L over partial R. So partial L over partial R can be similarly evaluated by 1 over 2 M partial over partial R, and we have got what is L as before. It is R square theta dot square plus R dot square. Okay, so it is R square theta dot square plus R dot square, and partial VR over partial R. So which becomes 1 half M 2R theta dot square minus partial VR over R. Okay, so it means that the partial L over partial R is given by, if you can cancel 2 and 2 from there on the right hand side here, 2 goes away with this, and you are left with mr theta dot square minus partial v r over partial r. I call this, okay, so if I have got m square theta dot 2, this is 2, and call this 3. Okay, now there is one more remaining. So the one more remaining term is partial L over partial theta. Okay, so which becomes partial L over partial theta is given by partial over partial theta is 1 half m r square theta dot square plus r dot square minus partial v r over partial theta, which goes to 0. Okay, and here it is equal to 0 because theta is not involved in this right hand side. Okay, so we can say that, note that theta is a second coordinate, is the second it is an ignorable coordinate as it does not appear explicitly in the Lagrangian, as it which you can see. Okay, now we consider the Lagrange equation again. So Lagrange equation says d over dt of partial L over partial qk dot minus partial L over partial qk is equal to 0. Okay, and for the first generalized coordinate, what we have, and qk okay, the first one is q1, which is r. Okay, uh, then the Lagrange equation becomes, then this Lagrange equation becomes d over dt of partial L over partial r dot minus partial L over partial R is equal to 0. Okay, so which means that d over dt of now partial L over partial R dot, which you have just calculated, is here. It is m r dot from 1. Okay, so this is, so if you simply substitute, partial L over partial R dot is equal to m r dot. Okay, and this is given by, if I take the partial L over partial R, right? And what is partial L over partial R, which we have also calculated? Partial L over partial R is here, mr theta dot square minus partial V over partial R from 3. Okay, so is equal to m r theta dot square minus partial V r over partial R, and using equation 1 and 3 above. So now if you consider this equation, it becomes time derivative of mr dot becomes mr double dot, and the right hand side is mr theta dot square minus partial V, which is a function of R over R. Okay, now this okay, just to let me represent that this part is the radial force for a conservative field. So this is Fr, radial force for a conservative field. So this equation then can be written as so mr double dot minus mr theta dot square instead I write down with the opposite signs. Okay, I write down in this way. So this part is Fr, radial force. Okay, so it means that I can write down m double dot r double dot minus r theta dot square is equal to, sorry, is equal to, yeah, is equal to Fr. Okay, okay, now this is the first differential equation which governs the behavior or the movement of that particle moving under the central force obtained by applying Lagrange equation. Okay, now consider Lagrange equation for the second polar coordinate, or second generalized coordinate. Okay, so this is the first one. So now consider Lagrange equation for qk is equal to q2, which is the second generalized coordinate theta, and for that use equation number 2. What is the equation number 2? Which is we have just written down here. Okay, so equation number 2, so use equation number 2 to obtain d over dt of partial L over partial theta dot, because q k is equal to theta, qk is theta, so theta dot here, and it should be equal to partial L over partial theta according to the Lagrange equation. So it then becomes d over dt of And now partial L over partial theta dot, which you already know what is given, we have already calculated that here, which is given by mr square theta dot, okay? So it is given by equation number 2. So mr square theta dot, okay? And this is equal to partial L over partial theta, okay? But one thing to note here, but mr square theta dot is the angular momentum of the particle which is moving under the central force. Momentum of the particle and we know that and the angular momentum remains constant, which means that d over dt of m square theta dot, mr square theta dot, okay, and this is equal to partial L over partial theta should be equal to 0 because this quantity does not change, okay, it's angular momentum. And this quantity we have obtained it to from above as the partial L over partial theta dot. Right, and this is partial L over partial theta is equal to 0, and this is also we obtain from above. If you make a reference here, you can see that, okay, partial L over partial theta, because it is theta does not appear explicitly in the Lagrangian here, so that's why partial L over partial theta is equal to 0 as we obtain here. So it means that the angular momentum, if you start with the what you have already obtained, that the Lagrangian does not contain theta, in that case partial L over partial theta is equal to 0, and the conclusion is that the angular momentum of the particle moving under the central force will remain constant. Right, so these are the two conclusions from the applying Lagrange equation to the analysis of a particle moving under the influence of a central force, right? And now we consider another application of this Lagrange equation, which is Atwood machine. So what this machine consists of is the following setting. So just going through that. So you can consider it to be a pulley with a string which can move two weights, okay, or you could say two masses. So here we have M2, M1, two masses, okay, and the radius of this pulley is A, Okay, let's consider this to be the horizontal axis, and the distance of this mass from this axis is x1, you can say, okay, and whereas the distance of this is relative to the horizontal axis is, okay, if the length of the string or we attach the two masses is L, so it will be L minus total length minus X. Okay, so L minus X minus half of the circumference. So here, okay, so it will be pi A, which will be X2. Okay, so this is the, and this can move up and down. So description is by X, and here we have the V is equal to 0, the potential, you can say the gravitational potential of the mass of the weight is given by to be 0 at that level. Okay, now what are the constraints on the movement of such a system? So let me, okay, so just the constraints. So let's look at the constraints now. So first constraint is given that the length of the string does not change, as you can see. Okay, the total length of the string is given by L, which is given by x1 plus the part of the string which is here coming the half of the circumference of the pulley, so it will be pi A plus the other part of the string which is x2 length. Okay, so this remains constant, okay, which is L. So L is given by this. So this is one constraint which you can easily notice here. And the second one is that the displacement of a pulley, or displacement of the weight with the mass m, okay, is given by the rotation of the pulley through an angle phi. So for instance, if you connect the center here with, this is the rotation, for instance, the phi through this angle, okay, then the x distance through which the mass will move will given by a phi, right? And so it means the velocity of that weight will be a phi dot, okay, which can be written as a omega, which is the angular rotational speed, okay, and phi of course is given in radians. Now the kinetic energy of Ke of this system, of this Atwood system, can be calculated. So if you look at the Atwood system, the kinetic energy can be calculated by, okay, let me calculate the kinetic energy as half mv square. So half of mass m and its velocity is x dot square, okay, and plus half m2 x dot square. Now you note that the velocities square, because this is the x direction, in the vertical direction is the x direction, okay, and here the velocity with which this mass moves up or down is same as this velocity where the mass m2 moves up and down. So the two velocities are identical, directions are opposite, but when you square that, okay, so it become direction does not count, so you only have x dot square for both of them. Both velocities are same, the masses are different. So this is the sum of the kinetic energies of the two. Now if you add to that the kinetic energy of the pulley itself, So what will be the kinetic energy of the pulley? We have already looked into that. It is given by half the moment of inertia times omega square. Okay, so this is the moment of inertia of the pulley I, and omega square is the rotational velocity. Okay, so this is the total kinetic energy of the Atwood system. So now if we look at, okay, now it can be reduced to half m1 plus m2 x dot square plus half I, now omega square, which you can obtain from here. It is given by omega given by x dot over a, so means that omega square will be x dot over a square. Okay, so I can write down x dot over a square. Okay, and also now the potential V, potential energy of the two. So because pulley is located at the levels where the potential energy is zero, so the potential energy is only of these two weights which are suspended by a string running over the pulley. So okay, so here the potential energy is negative because the distance is in the downward direction of these two pulleys. So the potential energy of this one will be minus m1 gh, and this one will be minus m2 gh. Okay, so there are two potential energies of these two masses, so which we can write down as minus m1 gx, right? And this is the distance of the mass m from the x, so this distance. Okay, and then this will be x2, so which can be written as L minus x minus pi a. Okay, so what you do is that the second can be written as, so I can write down as minus m2g x2, which is minus m1g, sorry, this is x, uh, so x2, instead of x2 I can just write down the expression for that. Okay, whatever you have written, because we are writing this to be x, so just write it as x minus m2g, and this is, sorry for that, so just ignore that and write this as such. Okay, so this is so I just write down as m2g and that distance. Okay, so this distance here, L minus x minus pi a. Okay, so this will be given by L minus x minus pi a. So L minus x minus pi a. This is what we have obtained. Now the Lagrangian is given by L, which is t minus v, and it can be calculated by, if you take the t from above, so it becomes half m1 plus m2 x dot square In fact, if I combine the terms together, the two terms together, I can write them as in a more compact way by putting I here over a square and then put that in the bracket. In fact, this half can also be put it in here, so I can put this bracket here. Let me put it in this way. So this is, and take x dot square outside from above. Okay, and then add uh, this minus v, there are two minuses, so I can put that as minus, becomes plus m1gx plus m2 g L minus x minus pi a. So this one can be now rewritten as, so this is the L. So it can be written as half m1 plus m2 plus I over a square x dot square plus m1 minus m2 gx m2g L minus pi a. I can rewrite it. Okay, now where x is the single generalized coordinate, of the system. Now the Lagrange equation can then be written as Lagrange equation is d over dt of partial L over partial x dot is equal to partial L over partial x, because this is the only. Now if you look at partial L over partial x dot, it comes out to be half, if you calculate that, it comes out to be half m1 plus m2 uh, plus I over a square 2x dot. Okay, 2 can go away with 2, so it becomes m1 plus m2 uh, plus I over a square times x dot. Now here and partial L over partial x, if you calculate, it becomes m minus m2 g, and the Lagrange equation takes the form it is d over dt of partial L over partial x dot is equal to partial over x. So now we can see that it takes the form d over dt of m1 plus m2 plus e over a square x dot and m1 minus m2g. Okay, so now if you solve this equation, this is a time derivative of x, so this then becomes this double dot here. So if you solve this, you can easily obtain an expression for x double dot, which is the acceleration of the two masses or weights suspended with the pulley, which come out to be m1 minus m2 g over m1 plus m2 I over a square. Okay, so this is the acceleration of the system. So you have found the acceleration of such Atwood system of two pulleys two weights suspended with a pulley by a string using or applying the Lagrange equation. Okay, so if you have got questions, please let me know. Thank you. Right. Okay, the denominator. So I'm just going back to, uh, yeah. So the denominator is I over a square. So it is m minus m2 times g divided by this whole thing, which is m plus m2 I over a square. So just if we want to, this is a square, okay? And this whole thing is the acceleration of the system. We're supposed to have m1 plus m2 plus, no, are you sure? Ah, okay, just a second, I am just going through. Yes, you're right. Yes, I can see that, yeah. Yes, you're right, yeah, there is a mistake there. I need to correct it, yes. This is a plus here, not not product. Thank you for correcting. So this is definitely true. Yeah, okay, let me, okay, so here, as you are saying, so it should be, I need to correct this. Thank you for that. So it will be, uh, so it will be m plus m2 uh, sorry, plus I over a square. Okay, so I don't need even that left big bracket then. Okay, so this one. Okay, thank you for correcting it. Thank you. Yeah, see you in the next lecture. Okay.